Humans have impacted Earth on a scale that few other organisms have throughout the planet's history. Humans are likely one of the most widespread mammals on the planet, accounting for around a third of the total mammal biomass. Our diverse built environments dramatically alter the way ecosystems function. Our consumption of natural resources and production of waste have impacted environmental systems even in areas far from our settlements. This worldwide environmental impact makes us unique amongst animals, and is rooted in our intelligence and the knowledge we have gained over the millennia. In this video, we will begin to explore this impact from a purely scientific lens. We will take a general survey of the crisis as a whole, and a bit about each of its complex parts, before going into a more detailed discussion of each issue in the next several episodes. Much of the technology and science that is behind our impact on the environment can be traced back to the Industrial Revolution. The Industrial Revolution, which was rooted in the Age of Enlightenment, is generally considered to be the period in which our impact on the environment began to grow exponentially. The technology we developed during this era allowed us to benefit and profit from the extraction of natural resources on a scale never seen before. Our innovations during this time also allowed for the explosion of human population that began around the mid-1700s. From these points, scientists have concluded that the modern human-environment relationship emerged during the Industrial Revolution. Accordingly, when environmental scientists considered how the Earth has changed due to human impact, we generally compare pre-industrial age data to post-industrial age data. The impacts humans have made on natural systems have indirectly led to the generation of environmental issues, some of which you've probably heard about, such as climate change and ocean acidification. Collectively, I will refer to these issues as the global environmental crisis. The fact of the matter is that even if you have heard of climate change or ocean acidification, few of us even have an outline of the mechanisms behind them and their impacts on the environment. In addition, these are just 2 out of the roughly 9 principal environmental issues that scientists have been studying. As students of environmental science, we must then understand the environmental crisis at a level that is somewhat deeper than is the norm for environmentalists. We must understand not only the complexity and intricacy of each issue that we have caused, but also the complexity of the crisis as a whole. Before we begin to explore the environmental crisis, we must first understand just what the environment is from the perspective of modern science. From a scientific viewpoint, the environment is simply the collection of all non-living and living things that exist on Earth. The environment can be broken down into several different levels or spheres. The biosphere is the total collection of living things on Earth. It is the sum of all ecosystems on the planet, the ecosystem of all ecosystems. The hydrosphere is a combined mass of all water on Earth, which is almost entirely found in the form of salt water. I'm not kidding about this. About 97.5% of the water on Earth is salt water. This little fact will be especially important when we begin to discuss the issue of freshwater use. The hydrosphere also includes all the water in rivers, lakes, wetlands, glaciers, and groundwater. Oftentimes, the portion of Earth covered by frozen water, like ice, permafrost, snow, and glaciers, is termed the cryosphere. The atmosphere, as you know, is a layer of gas and aerosols that surround the surface of the Earth. The chemical composition of the atmosphere plays a big role in the environmental crisis, so we will be hearing a lot about atmospheric chemistry throughout this series. Finally, the geosphere is the solid Earth below our feet, the lithosphere, the mantle, and the Earth's core. Although the geosphere will play only a supporting role in our discussion of the environmental crisis, it is nevertheless important to mention. These terms are all widely used in environmental science, so it may be a good idea to become a bit familiar with them as you are beginning to explore this discipline. In the last 2 decades, the environmental crisis has received an ever-increasing amount of attention from the international scientific community. The interdisciplinary field of environmental science has brought together biologists, oceanographers, atmospheric scientists, geologists, and many other specialists who have all contributed to our understanding of the Earth's system and how we impact it. The reason environmental science is so interdisciplinary is that the environmental crisis manifests and affects the Earth on all the levels we were just discussing. The planetary boundaries model is one of the most important and widely known models in environmental science. It will serve as an extremely helpful visual tool as we begin to explore the environmental crisis. This model, which was first designed by a group of scientists in 2009, proposes that humanity has a safe operating space in which we can impact the Earth system without this impact leading to severe consequences on its functions. The actual model is composed of 9 boundaries, or tipping points, each of which represents one of the 9 core environmental issues that threaten humanity. Tipping points are an extremely important concept in environmental science, as they illustrate the complexity of the Earth system, as well as the importance of having a working understanding of our impact on it. A tipping point is a critical threshold that, when passed, can lead to dramatic and irreversible changes in a system. These changes may be entirely nonlinear and, instead of causing some sort of alteration that we can predict, may instead simply increase the unpredictability of the system as a whole. An example of a tipping point in the climate system would be the melting of the ice sheet in Greenland, which could potentially alter the thermodynamics of the Atlantic and increase the global sea level by as much as 7 meters. In the planetary boundaries model, these tipping points are expressed quantitatively through a certain value related to each environmental issue. For example, the tipping point of the climate change boundary is measured in cumulative atmospheric CO2 concentration. Through this value, the scientists behind the model are expressing that at a certain CO2 concentration, the climate system will pass a tipping point, leading to irreversible and severe consequences. Another important concept in environmental science is feedback loops. A feedback loop is a process in which the output of a system impacts the input just as much as the input affects the output. In other words, what comes out of the system affects the impact of what goes into the system. Take a second to try to process this. A negative feedback loop is a process through which the output of a system tends to counteract the effects of the input. An example of this can be found in ecology. When a large population of rabbits eats most of the foliage in an area, this leads to a decreased food supply for these rabbits, causing their population to decrease. This decrease in population leads to a decrease in the amount of foliage that is eaten by the rabbits. The input, rabbits eating a lot of plants, leads to a reduction in rabbit population, leading to less foliage being eaten. In general, negative feedback loops tend to push a system towards stability, as the output of the system has a dampening effect on the input. In contrast, a positive feedback loop is a process through which the output of a system amplifies the input. All the musicians out there probably noticed an example of positive feedback. Whenever a microphone speaker system is having audio feedback, the output of the speaker is amplifying the input of the microphone, which then feeds back to the microphone and is again amplified by the speaker. Audio feedback is truly a textbook example of a positive feedback loop. An input is added to a system, resulting in an output that feeds back into the system, amplifying the original stimulus. Systems that contain positive feedback loops tend to be sensitive, and will quickly destabilize when a certain level of input is reached. Here is the main connection between feedback loops, tipping points, and the planetary boundaries model. Many of the boundaries of the model are simply quantified representations of the tipping points at which positive feedback loops may be triggered. In other words, the planetary boundary model is a framework This shows us how close we are to passing tipping points that would quickly cause certain aspects of the Earth system to spiral out of control, as if it was ever in control. In my opinion, the planetary boundaries model is an extremely important concept, as it synthesizes our current knowledge about the environmental crisis, while also being constantly updated by modern science. It is significant to mention here that the actual status of each boundary is hotly contested, and many of the scientists have disagreed with the quantitative limits that have been proposed for each boundary. This shows that this model shouldn't be considered to be a static representation of our progress towards environmental catastrophe. After all, the Earth system is much more complex than that. Rather, we should use the concept of planetary boundaries as a framework that we can update and alter according to scientific consensus and advancement. It is also important to note that although each boundary is visually represented in the model as independent, they're all connected, each having a positive or negative influence on all the others. It could even be argued that each issue can't really be studied as an independent boundary, but as a network of environmental issues that all impact the other. As you may be able to tell, there is still a lot of work to be done in order to even get close to understanding the environmental crisis. Now that we have all that introductory material out of the way, we can move on to the actual boundaries of the planetary boundaries model. The first boundary of the model is stratospheric ozone depletion. According to the model, this boundary is not passed. Ozone is a gas found mainly in the stratosphere, where it forms the ozone layer. Here, ozone absorbs incoming UV radiation from the sun through a series of chemical reactions. Due to this characteristic, the ozone layer essentially acts as a giant blanket around the Earth, protecting it from much of the UV radiation coming from the sun. Ozone depletion occurs when certain man-made gases are released into the atmosphere, where they can react with and break down ozone. In the early 1980s, scientists were beginning to understand the effects that these man-made chemicals had on the ozone layer. Soon, a scientific consensus emerged that these chemicals were causing a decrease in ozone concentration in certain areas of the ozone layer, which were soon termed ozone holes. In areas below ozone holes, which lacked the protective layer of ozone, greater amounts of UV radiation hit Earth's surface, causing various issues for the organisms that live there. International governance responded relatively quickly in what became known as the Montreal Protocol, which is widely considered to be the most successful international environmental policy to date. Even today, however, the ozone holes that opened in the late 1900s are still impacting the climate and pose a serious public health concern. The second boundary is ocean acidification. According to the model, we have not yet crossed the tipping point for ocean acidification, but we are rapidly approaching it. Widespread ocean acidification is a phenomenon that has occurred quite dramatically many times throughout Earth's history, each time leading to catastrophic impacts on marine organisms around the world. The basic reaction behind ocean acidification occurs when atmospheric carbon dioxide, or CO2, is absorbed into the ocean, leading to a reaction that creates an acid. The creation of this acid, as you may be able to guess, increases the acidity of the ocean. Since 1751, the ocean's acidity has increased by about 30%. Increased ocean acidity negatively impacts the ability of aquatic shelled organisms to form their shells. Non-shelled marine organisms are also impacted by ocean acidification through other physiological changes, many of which are currently being researched. Ocean acidification is a boundary that is extremely tied to climate change, as we will see, because both are caused by an increase in atmospheric CO2 concentration. The third boundary of the planetary boundaries model is freshwater change. This boundary has been recently broken up into two sub-boundaries: freshwater use, which is not transgressed, and green water, which is: humans rely on liquid fresh water, which is relatively scarce on Earth, for a plethora of different reasons. We mainly rely on rainwater, rivers, lakes, and underground aquifers to get the water we so desperately need. Only about 2.75% of the water on Earth is fresh, and about 1.75% of this 2.75% is trapped in glaciers, ice, or snow. The lack of available fresh water on Earth has been a problem for humans for all of our existence, and is exactly why most, if not all, of the largest cities on the planet have been placed near or next to rivers. Unluckily for us, the rivers most of us live next to don't provide us with enough water on a consistent basis. We have therefore become increasingly dependent on underground aquifers to get the water we need. Even more unluckily for us, these aquifers simply aren't filled up nearly fast enough to keep up with our rate of extraction. Freshwater use is therefore an issue of over-extraction. There's so many people on Earth who all need water, and there's simply not enough accessible waters in certain areas to keep up with these demands. Green water is water available to plants in natural areas. A recent study has suggested that, based on evidence of widespread changes in soil moisture, plants have access to a concerningly low level of water. Based on this study, the scientists behind the planetary boundaries model have added a green water boundary and have deemed this boundary crossed. The fourth boundary of the planetary boundaries model is climate change, which is considered transgressed. This environmental issue is likely the most widely discussed on Earth, and one that, without a doubt, receives the most attention from the media and the lay public. Accordingly, it is the most studied issue and, probably, the one we know the most about. The emission of carbon dioxide and other greenhouse gases into the atmosphere, mainly due to the burning of fossil fuels, has led to the warming of Earth's surface due to the greenhouse effect. This increase in the average surface temperature causes the expansion of deserts and causes wildfires, heat waves, intense storms, temperature extremes, and droughts to become more common, although the distribution of these impacts is uneven around the world. All ecosystems around the globe will be impacted by climate change due to their sensitivity to changes in climate. Climate change is considered to be one of the, if not the most, concerning environmental threats to humanity and perhaps all life on Earth due to its wide-ranging effects in every region on the planet. The fifth boundary is land system change, which is also known in the scientific literature as land use change. Land system change is the process through which humans alter the natural functioning of ecosystems through development. Most of the Earth's surface is directly impacted by human development. This is primarily driven by agricultural expansion and intensification. According to a recent study, around 3/4 of Earth's surface is currently developed by humans. However, it is important to recognize that all of Earth's surface has been impacted by human development, although mainly in ways that are challenging to see. Directly disrupting the functioning of ecosystem impacts both the biodiversity of the region and the ecosystem's ability to provide the services that we depend on. Land system change, therefore, increases the severity of all the other environmental issues we've been discussing, as it decreases the environment's ability to regulate and maintain its interconnected systems. The sixth boundary is biosphere integrity, also known as biodiversity loss. This boundary, like freshwater change, is broken down into two sub-boundaries: genetic diversity, measured in extinctions per million species per year, and functional diversity, which has not yet been quantified. Biodiversity is considered to be the measure of the integrity of the biosphere, as more biodiversity equals more stable ecosystems, as we spoke about a lot in the previous episode. Research has estimated that the current rate of species extinction is somewhere between 100 to 10,000 times the rate of background or natural species extinction. Biodiversity loss is mainly driven by landscape modification and acts as a detriment to the functioning of ecosystems and the services they provide. This boundary is one that is obviously tied with land system change, due to the fact that large tracts of land with little to no human influence are necessary for maintaining high biodiversity. Just like with land system change, biodiversity loss increases the severity of all other environmental issues, due to the fact that biodiversity is necessary for ecosystem services, which support the stability of the Earth system as a whole. The seventh boundary of the planetary boundaries model is biogeochemical flows. Although biogeochemical may seem like a complicated term at first glance, when one breaks it down to its constituent parts, it is really quite easy to understand. Bear with me here. Biogeochemical flows are simply pathways through which chemicals cycle through the living, bio, and the non-living, geo, systems. This boundary quantifies the severities of disruptions to the nitrogen and phosphorus cycles, which are fluxes to regulate the amount of these nutrients in the environment. Nutrient pollution has mainly been caused by the use and overuse of synthetically produced fertilizers. Excess reactive nitrogen and phosphorus in an ecosystem can lead to an explosion in the population of certain producers, such as algae, whose growth is limited by the availability of these nutrients. This explosion could have cascading impacts on the marine food webs in areas suffering from extreme nutrient pollution. Generally then, nutrient pollution has the capability of disrupting marine ecology in many coastal areas, where fertilizer runoff leads to massive algal blooms. We'll be talking a lot more about this in our episode on nutrient pollution. The eighth boundary is novel entities, also known as pollution. This boundary defines the amount of man-made chemicals we have introduced into the environment, excluding those in the atmosphere and nutrient pollution. It also includes the chemicals that we have introduced in the environment in quantities far exceeding their natural prevalence, such as heavy metals. Although this boundary has been deemed passed, it has not yet been quantified due to this issue's complexity and many-sidedness. In fact, it is quite difficult to make the argument that pollution should be contained within one boundary. Water pollution, inorganic pollutants, and organic pollutants are all very different issues with different impacts on the Earth's system, and could probably be made into boundaries of their own. Nevertheless, in the current planetary boundaries model, they are all grouped together as novel entities. As modern humans, most of us are all too accustomed to the chemicals and materials humans have introduced into the environment. Some of the most impactful and widespread of these materials are plastics, which are practically ubiquitous around Earth, from the peaks of the tallest mountain to the shores of the most remote islands. An estimated 3.6 billion tons of plastics have been produced, only around 21% of which have been incinerated or recycled. Plastics have various impacts on living things, most of which are caused by the blocking or filling of organs with plastics. Although efforts have been made to reduce our plastic production and consumption, the modern world still depends on them in countless ways, and it is unlikely we will be able to get rid of them unless serious and dramatic changes take place. Novel entities also include heavy metals, pharmaceuticals, and other organic chemicals used in industry. There have been around 350,000 different chemicals released into the environment, most of which have environmental and public health impacts that we have no idea about. The ninth and final boundary of the planetary boundaries model is atmospheric aerosol loading, or air pollution. This boundary has not yet been quantified, mainly due to the uneven distribution of this issue in different areas around the world. Anthropogenic air pollution includes both gases, such as ammonia and carbon monoxide, and particulate matter, which are microscopic particles of liquids or solids suspended in air, such as smoke or dust. These pollutants can cause allergies and respiratory diseases in humans and other organisms, depending on the pollutant. Air pollution is especially an issue in industrialized areas, as most pollution comes from industry and automobile exhaust. Air pollution is probably the most directly harmful environmental issue to human health. Between 7 and 9 million people die from air pollution every year. So there you have it, the 9 main environmental issues we face, according to the Planetary Boundaries model. As you are probably thinking right now, the environmental crisis is an extremely alarming web of issues, to say the least. I think it is quite obvious that it must be treated with the utmost seriousness in the years to come. As all of these environmental issues become more dire, they will have more severe consequences on the functioning of ecosystems. Degraded ecosystems, as we have learned, provide fewer ecosystem services than healthy ones. Therefore, the further we cause the degradation of the biosphere, the harder it will be for the biosphere to recover. This, combined with the very real public health threat of environmental issues, leads to a concerning and quite terrifying situation. However, it does us no favors to lament over our incoming doom or to indulge in alarmism. The only way for us to decrease our impact on the environment is through pragmatic and serious, but realistic, changes on all levels of our society. Nihilism and existential anxiety has no role to play in this pursuit. Instead, as environmental scientists, we must work to gain a more complete understanding of the crisis, educate others about its relevance, and push for changes at a regional, national, and international level. Another important point to make is although the environmental crisis is a significant concern for humans, the Earth as a whole will be just fine. To protecting the stability of the Earth system, we are in fact protecting the stability that so sustains our society. Even if the Earth system descends into further instability, the planet will eventually recover. Although many mainstream environmentalist platforms will have you think otherwise, the Earth has actually gone through many dramatic environmental catastrophes throughout its history, many of which were much more severe than the ones that we are causing. The truth is that Earth's system has never been perfectly stable. There have been particular events throughout Earth's history, termed extinction events, where biodiversity on Earth has dropped rapidly and dramatically. The brilliant thing about life is that it keeps on living. Even if it takes hundreds of millions of years, biodiversity has always recovered from these extinction events through the processes of evolution. This is the fact of the matter. It is extremely unlikely, as in basically impossible, that humans will ever be able to wipe out all life on Earth, even if we tried. No matter how much our system may screw things up, regardless of how long it takes for us to become a more eco-friendly species, the Earth will recover and life will go on, even if it's without us. That's just the way evolution works. However, the issues that humans are responsible for have the capability of disrupting the very stability of the planet that our global society depends on. With less biodiversity and severe environmental imbalances, the fabric that underlies our civilization will become increasingly unreliable. The most concerning thing about this is that this process is already occurring before our very eyes. We just haven't noticed it yet due to the shortness of our lifespans. This is why it is so important, more important than ever, to learn about the environment and how we're impacting it. As you continue your studies of the environmental crisis, it is also important to recognize the motivation you have for this pursuit. For most of us, I'm sure the reason we are studying the environmental crisis is that we are passionate about the environment in some way, shape, or form, and we want to protect it. In my opinion, this love for nature is exactly what can keep us motivated and grounded as we traverse the dark waters of the crisis. Oftentimes, the things we learn through environmental science can be quite worrying and downright depressing and overwhelming. If we keep our love for nature at the forefront of our minds at all times, we will be able to understand why our studies are so important, even if they may bring us to face some terribly concerning facts. It seems like a great burden to be placed on our shoulders, and it may, in fact, be the greatest existential threat humanity has faced. But with collective effort and innovation, anything is possible. The key is to play a role in this collective effort and innovation in the present, instead of hoping that someone else will fix the problem. As I've said before, the first step toward action is awareness.